All right, so what we want to do today is look at the precise definition of a limit. In our book, this is section 2.5. This is not, I think, an easy concept conceptually. So let's go ahead and look at the precise definition of a limit. In order to really go forward with this, what we want to do is understand what it is that we're doing, because it's very easy just to get lost in a big mess of symbols and to feel like nothing is really going anywhere, and we already know what a limit is. Okay, so the way that we designed this chapter is first we figured out how to get an intuitive sense for a limit, and we looked at some graphs and pictures, and we experimented numerically. And then we looked at how to work with limits algebraically. And then now at the end, we're going to come to a formal definition of a limit. And typically we start by defining things, right? So this is kind of backwards. And it's because this formal definition is very complicated. So what we want to do as sort of a mental exercise to prepare for going through this is to realize that you already know what a limit is, that before you start this section on the precise definition of a limit, you know what a limit is. What we're trying to do is figure out, how do I write things precisely using mathematical language that we already sort of understand. Okay, and making that connection is going to be very helpful to sort of grow as a mathematician. Okay, so what we're going to do before we jump right into the definition is look at some preliminaries. And what I want to do is look at, what does it mean for things to be close? Okay, two numbers being close together is an easy concept, but it's kind of hard to write down mathematically. So here's what we're going to do. Let's start by looking at two numbers on a number line. So let's suppose that here's my number line, and I have two numbers on here. A and B are two numbers. And I want to look at how far apart they are, right? Their distance. Okay, well, if these were numbers like 3 and 5, I know that 3 and 5 are 2 apart because I could just subtract the numbers to see how far they are apart, right? How much do I have to, what do I have to add to A to get to B? Okay, so the distance between them is B minus A. And when I write things like A and B, I don't really know which one is bigger. If I just write an A and a B on here, right? Because they're unknowns. If I write like a 3 and a 5, I can say, oh, take 5 minus 3 because 5 is the larger number. So when I subtract, I'll get a positive. Okay. Distance, we always want to be positive, and if I don't know what the numbers are ahead of time, I don't know which one is bigger. And so when I subtract, I run the danger of getting a negative, and that's why we use absolute value. Okay. So the difference will give me the distance, and the absolute value makes sure that it's positive. So this distance is the absolute value of B minus A. Okay. So if I see a mathematical statement like this, the absolute value of B minus A equals 3, I can say the distance between B and A, or you could say it the other way, the distance between A and B is 3. Okay. We can also use an inequality to let me know that things are within a certain distance, right? So if I write the absolute value B minus A less than 3, then we can say the distance between B and A is less than 3. Or another way of saying it is that the number A is within 3 units of B. So let me look at what this would look like on a number line. So maybe here's my number B, and I can say, all right, go out a distance of 3 units. Okay, so if I know that the distance between A and B is less than 3, then I know that A lives somewhere inside here. Okay, now if I know what the number A is, I can just plot it on the number line, but sometimes we want to look at an unknown or a variable. Okay, and one of the things that we could do is, instead of thinking of A as just being something that's unknown that we're trying to find, we can also think of it as a variable, right? So we could look at numbers X that are within 3 units from the number A. So instead of saying, okay, there's this one number out here and I'm trying to find it, we could instead say, okay, here's A, and I want to measure a distance of 3 away in either direction. Okay, and then when I write absolute value of x minus A is less than 3, then the x's that make that true are all the x's in that interval. Okay. So the x in here are the x from over here. Okay. And sometimes we might want to exclude the number A. We want to say, all right, I want to look for all of the x's that are within 3 of A, but not A itself. I don't want to think of A as being one of those. Okay. And then that means that I just want the distance to not be 0. So we could just say, well, the distance is greater than 0. Okay. So this part over here on the left, we write this to exclude A from the set. Okay. So this is giving us some formal language to talk about distance and closeness. I can talk about being, what all the numbers that are close to, right, or in this case within a distance of 3 from A, except A itself. And this is the idea that we want to get at for a limit, because we want to look at what happens as I get really close to a number, right? If I'm looking at the limit as x approaches A, I want to look at numbers as I get really, really close to A. And this is giving me some process for doing that. And of course, we know with a limit, we want to exclude what happens exactly at that x value. And that's why we talk about this, right? We're going to see that involved. All right. Now I think we're ready. Let's go ahead and, oh, no, sorry. One more piece. This isn't like something new. We've used all sorts of letters for variables before. But these two are going to be really common. So we have these two Greek letters that are very commonly used in mathematics to denote a small distance. So the first one that we want to talk about here is the lowercase Greek letter epsilon. And we're going to use this for distances on the y-axis. Okay, so I'm still thinking about things being on a number line, but this is going to use the y-axis as my number line. Okay, so let me just real quickly draw a little graph. Suppose I have some function of x, and I have y values going up the x-axis, right? Right. Maybe one of these values is L. Okay. And I can think of values of f of x as being like y values. Okay. So we can think of epsilon as being a distance on the y-axis. So if we write f of x is minus L is less than epsilon, going back to our language from before, what we're saying is I'm looking at the f of x values that are within a distance of epsilon of L. Okay. So if I have my little distance epsilon here, then I'm looking at y values that are between these green dotted lines that I have crudely drawn. Okay. Delta is a lowercase Greek letter that we're going to use for distances on the on the x-axis. Okay, so if I have a similar looking graph here, and I have some a value on the graph, suppose a is over here. Okay. 0 less than absolute value x minus a less than delta means we want to look at the x values that are within a distance of delta from a, excluding a itself. Okay. So what I'm going to look at are, not including a, I'm going to look at all the numbers that are within a distance of delta. Right? So I get like this interval here with a hole in the middle. And what we're going to do when we look at our definition is have a hole in the middle when we're looking at x values, because we want to ignore what happens exactly at a when we talk about a limit. But that's not going to happen on the y-axis. We're not going to have anything that we exclude there. All right, let's get into our actual definition now. So here's our definition of a limit. Let f of x be defined for all the x values except for a on an open interval containing a. Let L be a real number. Okay. And what I'm going to do is I'm going to go through this a couple different ways to try and make sense of it. But we're just going to look at this definition and then try to pick it apart. Okay, so this thing that we know of and have written as a limit, the limit as x approaches a of f of x equals L, means that if for every number epsilon that you pick, every positive distance that we can measure on the y-axis, then there has to exist a distance on the x-axis such that if I pick x's close to, using delta as my distance for closeness on the x-axis, then my y values are going to be close to L, where epsilon measures my distance on the y-axis. Okay. So maybe writing this out another way. So if you pick a number epsilon, okay, and as your measure of closeness on the y-axis, okay, then I can find a close enough measure, right? So a number delta, so that if x is close using delta, to a, then f of x will be close to L using your definition of epsilon. Okay, so what I want to do is I want to look at a picture of this and hopefully understand how these pieces fit together. And then we want to come back and look at it and see, does this really give us this idea of infinitely close, or are we just putting in some numbers? Okay, so let's look at some pictures. And what I'm doing here is we're going to look at this as a progression. Okay, so think of this first one as having picked a number epsilon. Okay, so in this first one, epsilon is this big. So we picked a number epsilon. Maybe it was like 1/2. And maybe you say, okay, yeah, if you're within 1/2 of L, that's close enough, right? Just say, think of rounding to the nearest whole number type of thing. Okay, and so what we want to do is say, all right, are my y values getting close to L? Where close to means within 1/2 of. All right, and then what we do is we say, all right, that means that we have to pick x values that are close to A. So we find a number delta, right, a closeness to A, based on that flexibility that we had of 1/2. And so what we do is we say, all right, well, you know, I can pick a number here. That's within my epsilon of L. And that gives me a point on the graph that is that far away from A. So I have to make sure that I pick a delta that keeps my x values close enough to A that I don't accidentally pick something out here, right? If I pick something out here, my y value would be too far away from L. Okay, so we need to pick deltas that keep our x values reined in, that keep them close. Okay, so we want to pick a small delta, right? If I pick a smaller epsilon, if epsilon, instead of being 1/2, let's suppose epsilon is like 0.1, right? It's a smaller number. Then we have to be closer to A, right? We need a smaller delta. Okay, so let me give you an example. You know, using a real graph, and we're just going to plug in some numbers and figure out what like an epsilon and a delta might look like with concrete numbers. Okay, so let's suppose that here's my graph. I'm going to graph y equals x squared. Okay, and what we want to do is analyze the limit as x approaches 2 of x squared equals 4. Okay, so in this case, A is equal to 2, L is equal to 4. And what we're going to do is say, well, let's see if this is true, or let's kind of walk through the definition here, or at least part of it. What does it mean for my function values to be close to 4, right? So let's suppose we pick an epsilon that's equal to 0.1. Okay. So if I look at the statement f of x minus L is less than epsilon, I can replace all of these pieces because I know what they are. I know the function f of x is x squared. I know that my L is 4. I know that my epsilon is 0.1. So we're looking at all of the values of x squared that are within 0.1 of the number 4. Okay. So all x that make x squared within 0.1 of 4. Okay. So what would that look like, right? So let's suppose that here's 2. That's my x value. Suppose here is 4. So I can go as high as 4.1 and as low as 3.9, right? Okay, and all of these y values in here between 3.9 and 4.1 are within the epsilon that I've chosen of 4. So let's see, what would delta have to be, right? Well, let's figure where they are on the graph, right? So if I look down here, okay, what x value do I have to plug in so that my y is 3.9? Well, I can solve that. I can say, okay, x squared equals 3.9, and I can just take the square root to solve that. Okay, so I get x equals 1.9748. I'm just going to use 4 decimals here. What about on the other side? What about x squared equals 4.1? So I take the square root of 4.1, and we get 2.0248. Okay, what we want to do, we want to look at what that means in terms of distances. How close is that to the number 2? So how close to 2? Okay, so what we can do is we can subtract, right? I can take the distance between 1.9748 and 2 by subtracting. Oh, if you're just joining us, make sure that you're on mute until you have a question. Okay, so here the distance is 0.0252. Okay. For the second one, my distance is 0.0248. And those aren't the same distance, okay? What we want to do is pick a delta that will ensure that all of the x values within that delta distance are good x values. Okay? So if I pick my delta to be 0.0252, then on the left side, all of those x values will be fine. But on the right side, I'll have some that are too far away from 2, so that x squared is too high. It'll be above 4.1. Okay, so our delta has to be the smaller of these two so that it works on both sides. Okay, so if epsilon is equal to 0.1, we can pick delta equal to, I'll pick the smaller number, 0.0248. And then as long as my x values are within this tiny distance of 2, the y values will be within 0.1. Of 4, right, of our original x value. All right, so okay, let's look at another example. This time what I want to do is actually show a limit using that definition. Okay, so if I recall our definition, the limit as x approaches a of f of x equals L means that for any number epsilon greater than 0, there is a delta greater than 0 such that for the x values that satisfy this, right, 0 less than x minus a less than delta, then the absolute value of f of x minus L will be less than epsilon. Okay, the reason that this definition gives us this sense of infinitely close is because it has to work for any epsilon greater than 0. So the idea is that no matter what number you pick, we can find a close enough that makes this work. And so because we've built this into our definition that it works for any epsilon greater than 0, then, you know, if I can say that no matter how close you pick, right, something works, then that's kind of, that gets us this idea of infinitely close. Okay, so we don't have to deal with infinity directly. We have to say it works for any number. And if it can work for any possible distance, then it has to work for all the smallest distances you can imagine. All right, so let's go ahead and take a look at this. The way that we go through this, I'm going to have my scratch work on the left, and I'm going to have my formal proof on the right. Okay, so for the formal proof, what we're going to do is start with a number epsilon. So let epsilon be greater than 0. Right? So it's any number greater than 0. Okay, now I have to pick a delta based on that, and I need to figure out what that is. So I'm going to go back over to my scratch work, and here I'm going to work backwards. So what I'm going to do is I'm going to say, okay, what would this look like? Let's look at the ending thing. F of x minus L less than epsilon. Okay. My function f of x is 3x plus 5. The L is 11. And epsilon is just a number epsilon, right? So here I have my f of x. Here I have my L. Here I have my number A. So let's also write down the other side of that, right? We also have this 0 less than x minus A less than delta. Okay. Well, I know that the A is 2, so I'm going to have an absolute value of x minus 2. Okay. So let's just kind of work with the scratch work a little bit. Okay, I have this absolute value of 3x plus 5 minus 11. Well, 5 minus 11 is negative 6. So I have 3x minus 6 less than epsilon. And I can see an x minus 2 over here. So if I want to make a connection between the two, maybe I want to factor out a 3. Okay, and in fact, I can get it to look just like what I have over here if I divide both sides by 3. Okay, and epsilon over 3 is it's kind of a nice symmetry there, the symbols. So what we're doing is we're saying, okay, when I make these steps, when we do steps in algebra, they're typically reversible. But what we're doing is we're saying all the x values that make this statement true also make this statement true because we've just substituted in numbers that we know. And all the x values that make this second statement true make this third statement true because it's the same thing, right? 5 minus 11 is just negative 6, and so we've just rewritten it, right? And that's all we're doing is sort of rewriting stuff. So these are all logically equivalent. Okay, so it's the same x's that make each of these true. Okay, so if I start off by saying, all right, if you pick 0 less than x minus a less than delta, and we're allowed to pick a number delta, right? We want to pick delta equal to epsilon over 3. Okay, so let's see what that'll do for us, right? So if you pick any epsilon greater than 0, right, or if we let epsilon be any number greater than 0, pick delta to equal epsilon over 3 for this example. Then if I'm looking at x values that make this true, x minus a less than delta, then that's the same as saying x minus a is less than epsilon over 3. And I know that a is 2. Okay, and then I can just do the same scratch work I did backwards. Multiply by 3, distribute that in, rewrite 6 as plus 5 minus 11. So that tells me that 3x plus 5 minus 11 is less than delta, which means the absolute value of f of x minus L is less than epsilon. Okay, so what we're doing when we are showing this definition, right, when we're kind of going through this formal proof, is we're saying, all right, no matter what measure of closeness you pick using the epsilon, we can find a measure of closeness for the x's, right, the delta. that will make sure that our y values are close, right? And so we do our scratch work to find it by working backwards. And then we say, okay, that's the number that works. That's the delta that will clinch it, so that if my x values are close to a, then my f of x values will be close to L. Okay. Does that make some sense? If that makes total sense to you, that means you've probably had calculus before, because this is not something that I think when people are learning calculus the first time, when you get to this, you should be like, this seems very confusing. That's the normal reaction. I mean, I'm not saying it has to be everybody, but that's the normal reaction. You look at this and you're like, this is very confusing, and then you wonder, like, why are we doing this? And what it is, it's a growth, right? You know, we have to kind of get through this to grow our understanding of a formal definition, and you know, this idea of infinity and writing things precisely in mathematics instead of just, you know, everything being solving equations, right? So it's hard, and we'll go through another one of these. There was a mathematician, John von Neumann. I don't know if he's still alive. He was a contemporary mathematician, not like hundreds of years ago, but I think he might still be alive. I think he's the one who said, you know, nobody really understands mathematics. You just get used to it. So, you know, there's that. All right, let's try another example. Let's show that the limit as x approaches -3 of 6 minus 5x is equal to 21. Okay. We'll have our scratch work, and we'll have our, I called it a formal proof, or sometimes I say that this is the logic of our argument. Okay. So for the scratch work, we work backwards. We start off with what we want to end with. F of x minus L is less than epsilon. And we fill in the pieces. F of x is 6 minus 5x. The L is 21. And we see what we have, right? So I start combining stuff. So 6 minus 21 gives me a negative 15. Okay. And I can factor that. If I factor out a negative 5, well, let's hold on. It's not factored yet. Let's figure out where we're at. What I find is helpful is to see, well, where am I going, right? If I write the end, you know, the other side of this where I want to end up, I want to end up with x minus a is less than delta. If the a is negative 3, that's x minus negative 3 less than delta. Minus a negative is plus. Okay. So what I'd really like to see is an x plus 3 somewhere. I say, well, I've got a negative 5 in front of the x. Let's factor out a negative 5. So if I factor out a negative 5, I'll have 3 plus x. And when I factor it out with absolute values, right, when I have two multiplied things inside an absolute value, we can sort of, you know, pluck them out, but absolute value makes things positive, right? So when it comes out, it's the absolute value of negative 5 or positive 5. And I can rewrite 3 plus x as x plus 3. Okay. So then to get my absolute value of x plus 3 by itself, I'm going to divide both sides by 5. Okay, so I can see, this is what I want for delta. Okay, so then when we go through with the logic, we say, all right, for any epsilon greater than 0, pick delta to be epsilon over 5. Okay. then if 0 is less than x minus a is less than delta, then that means that, and I can ignore the 0 part. I don't really need it to show this next step. And I'll explain why in a second. But my a is -3, so I have x minus -3 is less than delta, but I'm going to write that as epsilon over 5. So that means that x plus 3 is less than epsilon over 5. And I already did this work with my scratch work, so because these statements work both ways, right? Divide both sides by 5, I can undo it by multiplying both sides by 5, right? I can say, all right, this means I can go all the way back up to the top, right? Using this work. To give me f of x minus L is less than epsilon. So that means the limit as x approaches -3 of 6 minus 5x is equal to 21. Okay, out of all of the sections that we do in the class, I think this one is going to be the most confusing. Now, when we look in the book, they have a lot of examples where you can look at more complicated functions that involve like squareds or one-sided limits or infinite limits. And there's nothing wrong with going through that. But I think that we get diminishing returns, right? I think if we try to just understand the simplest examples, that sort of takes us through this process where we have to symbolize the difficult mathematics, right? We have to look at how do I write down a simple concept like closeness and infinitely close. And looking at more complicated functions, I don't think is as much benefit, for the amount of time it takes. So we're gonna look at that. We're gonna leave that there, and maybe we'll come back and address this after I assign some homework questions on it, and we can look at those after you've had a chance to try them out. All right.